Now we're going to work on logarithms. So we're going to do not all of 12.3, but we're going to do a little bit out of 12.3 and a little bit out of 12.4, and then that'll be it for the quarter, so we're just about there. So I want to go ahead and start off with just the basics of logarithms. What is a logarithm? How do you work with it? Then we'll take a look at the graph, and then there's a couple of properties that we're going to work with. So just really those three topics. So I want to start off with, first of all, what is a logarithm? So there's a definition, but more than just the definition is really a formula for us figuring out what that means. So I'm just going to give it to you here. Log base b of x equals y means, and there's two arrows here because you can go in either direction, means, so let's unwind this. And I'm going to give you the language here. We read this as log base b of x. That language is so helpful because the base is b, which means when I rewrite it, I'm going to kind of unwind this. I write this as a base over here on the other side. B to the y equals x. So what a logarithm does is it solves for the power. So a logarithm is equal to, this is the base, let me back up, so that's the base, but the y is the power or exponent. So these logarithms give us a way of coming up with an inverse function for exponents. How do you undo an exponent? So really that's all it is. So a logarithm, let me spell that out, a logarithm is an exponent. If you can remember that, then you've got it. So star, 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 exclamation mark, whatever it takes, but a logarithm is an exponent. Okay, so there's that. So some examples. So what does this mean? So if we have log base, let's do log base 2 of 8. Remember, a logarithm is a power. So I want to simplify this. I want to compute this. So if 2 is my base, 8's kind of my answer. The question is 2 to what power, because logarithms are going to give us a power back, 2 to what power equals 8. So really, I can write this as 2 to what power equals 8? Answer is 3. So the logarithm gives me the power that gets me from the base to this. It's called the argument, but you can also just call it the answer if you're thinking of it that way. Notice how I wrote this out in two different ways using that definition. This first form is the logarithmic form. And the second form is the exponential form. And they are interchangeable, and so helpful to be able to go back and forth between the two. Okay, let's do some more examples just like this. So, example, log base 5 of 25 equals what? Well, what I'm really thinking through is I need a power. What power gets me there? So this says 5 to what power equals 25. So how do I get from 5 to 25? 5 to the second power. So my answer is 2. Oh, did I write a 2 there? Sorry. 3. 2 to the third power, back up to the last example. 2 to the third power equals 8. 3. On this one, it's a power 2. 2. Okay. So I messed you up, so let's do another one. Okay, so for example, log base 3 of 27 equals what? Let's see, I need a power that gets me from 3 to 27. Well, 3 to the second power is 9, so that must be 3 cubed. So 3 to the third power. So my answer is 3. Okay, how about this one? Log base 4 of 4. Okay, a logarithm asks for a power. So I can write it out. You can write it out too. So this says 4, that 4, to what power gets you to a 4? Well, it's not very exciting, but I just need a 1. A 1 will get me there. So the answer to that logarithm, when I compute it, is 1. Okay, so while we're looking at ones like that, how about this? Log base, I don't know, 7 of 1 equals what? Okay, again, logarithm is looking for a power. So 7 to what power equals 1? This is one of our properties from exponents. We need a 0 for that. 7 to the 0th power. 7 to the 0 equals 1. So the answer to that logarithm is 0. Okay, well, we've dealt with a lot of different kinds of exponents, which means I can keep going. How about this one? Log base, let's do log base 16 of 4. I can go from a larger base to a smaller answer or argument. Okay, so equals some number. This says 16 to some power equals 4. Well, the only way to get there with a power would be a square root, right? The square root of 16 is 4. Well, the square root is the same as a 1/2 power. Remember, and a cube root is a 1/3 power. Really great review from earlier in the quarter. So that's 1/2. You can't see that, but I'm going to put that over here in my answer box, 1/2. So you're looking for those bases to be bigger. So if I did log base, 1,000 of 10 equals, I forgot my empty spot, equals something. This would be 1,000 to what power equals 10? Well, I would need a cube root, wouldn't I? Because 10 to the 3rd power is 1,000. I would need a cube root, which is the same as a 1/3 power. So 1/3 is my power. Okay, how about this one? Here's another kind of exponents. Log base 3 of 1/3. Now I'm going from a whole number to a fraction. So how do we get that 3 into the denominator using a power? 3 to what power equals the reciprocal? I need a negative exponent. So this would be a -1 gives me that reciprocal already here where you can see it. So when you see a base that's a whole number, and then you see this argument that's a fraction, the only way to create a fraction is to use that negative exponent. Let's do another one just like that. Log base 2 of 1/4. Log base 2 of 1/4. Okay, so 2 to some power equals 1/4. Well, I need to get it reciprocated, which means I need a negative power. So I know I need the negative. That gives me the numbers in the denominator. But 4 is 2 squared. So I get a -2. I'll write it where you can see it. So a -2. Negative does the reciprocal, and 2 does the power 2. So as you start to work with logarithms, this is how you can think them through. You're just asking yourself what power gets me from the base to the argument. There's another special type of logarithm. So if I wrote log base 10 of 100, we could figure that one out. Let's see, 10 to the 2nd power gets me to 100. This one, because we're doing powers of 10 here, is called the common logarithm. So this one's a special type. So this is the common logarithm. And if you pick up your calculator, I do have mine, but I only have my fancy one. It doesn't have to be a fancy one. Any kind of a calculator. On my calculator, I have my logarithms over here. A lot of the scientific calculators will have their logarithm keys up here. They do the same thing. You'll notice that you have an log key. That's the common logarithm. It will do base 10. So if I do log of 100 equals 2, with some scientific calculators you'd want to type the 100 first and then hit your log key. Mine doesn't work that way, but some you do the number first and then your log key, so you have to play around with it. But notice there's no room for a base, and there isn't on any of the scientific calculators either. So your calculator will only do log base 10. That's all it does. So we have log base 10, and then if you look right next to your log key, you'll notice that you have an ln, and it's right next to this e to the x key. Usually those keys are shared. So an ln is another special type of logarithm. I'll write that one down. So example, let's see, log base e of x, I'm just going to write this down in general, is the natural logarithm. You can't see that. So log base e can be replaced with ln, which is the natural logarithm. And e is just a number that happens to be the perfect base to get things like anything that grows or decays in nature continuously just happens to be this number e, which is why it gets its own special number. So it's just this base that works for organic growth and decay. So very cool. So if you take, I'm going to put e in here. So if I'm going to do I'll show you what e is. So if I do it says e to the what? So I'll say e to the first power. It's just a number between 2 and 3. So it's 2.71828, and it goes on forever. But it just happens to be the perfect base when we do exponential growth or decay of something organic. So that's where that is. Okay, so that's the natural logarithm. So when you look through your book and you look through some examples, you'll see some things that have the ln in front, and you'll also see some things, I can rewrite this base 100 as just log. If I leave the base off, it's understood to be 10. So when I leave the base off, it's understood to be 10. These are the only two that are in your calculator. I don't care how much you paid for it. Those are the only two that are in your calculator. Let's also go backwards. So your homework has you go backwards as well. So let's do that. So let's start off with an exponential. So let's do 3 to the x equals 5. So if I want to write this as, so it would say something like it would say write the equivalent logarithmic expression. Okay, so I'm pulling these right out of the homework. And I'll get the homework adjusted. So you'll see some new homework assignments. They still won't be required. You can just use them for practice, but I'll choose ones that will be similar to what you'll see on the exam. So you'll have some really good practice, even though it won't count in your homework grade. Okay, so 3 to the x equals 5. So when I write it, I know that my base is 3. My exponent is x, so this is my power or exponent, and my answer or my argument is 5. So when I rewrite this in logarithmic form, it's log base, well it's going to be log base 3 of the answer equals the power x. So when it says write it in equivalent logarithmic form, that's exactly what you're looking for. Okay, here's another example. Let's say that we have e to the 3 equals 20.72. Okay, just making stuff up. So again, I would pull out, I need log base something. So this is my base, this is my power, and this is my answer. So when I put this together, I write log base e of my answer, 20.72, equals, power always goes on the other side, equals 3. But I've got one more step here. Because I have log e that has a special name, I can change that into the natural logarithm. So I write ln 20.72. So this isn't simplified form, the log base e. The ln is the simplified form. So ln 20.72 is equal to 3.